general form. Here we're just restricting our attention to the reactants. The general form is rate constant so these are the orders. This will be a 0, 1, or a 2. This will be a 0, 1, or a 2. This is the overall rate. I guess I'll say overall rate. But for instance, if I had this reaction and it was you can separate them like this. What this means is you have a first order reaction with respect to A and a second order reaction with respect to B. And you have an overall reaction that's a third order reaction because you just add those two exponents. Exactly what all this means, and I'll get to in just a minute. You with me there? Another thing to say is, well, I'll say the rate constant units. So let me go through an example that makes you actually use these. All right, so we focus here, and notice it tells you here, this reaction is a second order reaction with NO2. So we're going to have some K, that, and it was say a zero order CO2. So what is the overall rate equation? You can just take this, get rid of this. And that's actually the answer to this. I know it's abstract, but this so far is simple, right? It just looks abstract. The question here is, you're given this, and you're told it's second order with relation to NO2, and it's zero order with relation to CO2. So what's the overall rate expression? And you could write it like this, but I just got rid of the CO and I wrote it like that. So far this should seem abstract, but easy. You with me? I don't have the thing up, but there's just another one that you can practice. Okay, here's what I want to do now. I'm going to have to bring up slide 7. And what you need to be able to recognize, a lot of these show you data, rates of reaction versus concentrations. But notice, let me start here. If I have, considering the rate, and I'm going, here's my rate constant, and I have concentration of A, and there's a 1 here, I don't even have to write the 1. If this doubles, if as the reaction goes on, this doubles, or let's say it cuts in half, so I multiply that by 1/2, and this is a constant, what does that do to the rate? Just think in terms of algebra. Stick a 1/2 in here. What do I have to put over here for the rate? A 1/2. To follow the rules of algebra, if I'm just in theory going, the concentration cuts in half, and I calculate through, and that's going to say the rate cuts in half. Or we could say that that's linear. You with me there? Okay, follow me. This one, rate equals K. For this one, concentration doesn't show up anywhere. There is a concentration for the reaction going, it just doesn't depend on the concentration. So if the concentration halves for a zero order reaction, what happens to the rate? It doesn't do anything because there's no concentration here. Zero order doesn't depend on the concentration of the reactants. So now I'm actually getting out of the abstract part and explaining what this means.
I'm sorry, could you go over what constitutes a zero order, first order, second order?
These are found out by experiment. There's not, you can't just look at a reaction and go, okay, I know what that
So
is.
should we be given that?
Yeah, that's what this problem is. It shows you some data and then you're going to figure it out.
Okay.
But I got to explain this first. But realize zero order reactions, how fast they go doesn't depend on the concentration. First order reactions, it depends on the concentration. Second order reactions, it depends big time on. So this is the one where it sort of comes together. Concentration of A squared. If the concentration of A decreases by 1/2, how much does the rate decrease by? No, that was here. This one, I could just write this one out here because there's no square or anything. If I multiply this side by 1/2, or really I mean the concentration goes down by 1/2. That's a constant. This has to go down by 1/2. But if you square that, 1/2. And of course, third order reactions, we won't even do third order reactions, but it goes up and up and up like that. So this goes linear. Concentration and rate go linear with each other. This rate doesn't even depend, and that's a constant, so that just means the rate stays constant at zero order. For these, for a 1/2 decrease of concentration of A, you get a 1/4 decrease of the rate. Okay, that's all I have to say to look at this data. So look at the PowerPoint. Look at 7. And you've got the data. So look at the top left. You've got trial 1, trial 2, trial 3, trial 4. So somebody did 5 experiments. And they went, okay, at this concentration, moles per liter for NO, and this concentration for O2, it's O3. So those are the two reactants. I didn't put the reaction on here. That was the rate constant, 6.60 10 to the -5. All right. Now look at trial 1 and 2. The concentration of NO hasn't changed here. Their second trial, they kept the concentration of NO the same. But they bumped up the concentration of O3 by a multiple of 2. Do you see that? You can see that, right? 3 times 10 to the -4 times 2 is 6 times 10 to the -4. You with me? Now look at the rate. It went from 6.60 times 10 mole per liter per second. So what happens to the rate here? I've got this on my piece of paper. rate goes from, it's probably the power of 10s that make this hard to see. The rate goes from there to 1.32 times. I will mess up if I don't do it like that. So here's your first rate. And going from here to here, can you see that that's a multiple? You multiply this by 2, you get this. So that doubles. They work in tandem. One doubles and the other one doubles. You with me?
Where did you get the 6.60 times 10 to the
Look back up here at the data. I'm saying the first column, concentration stays the same. So it kind of like takes that variable out of your way. Now we're only looking at O3. Look at O3 here. 3 times 2 is 6, and they're both power of -4. And then look over here. That's the 6.60. You just asked me where that comes. That's the one in the far right column. That's the rate. The rate was this, and it went to this. And I just did this so you can see the zeros in order of magnitude easier. If you multiply this by 2, you get this. So both of them double. All my wordy word here is saying concentration of 3 doubled and the rate doubled. You follow me? If that's true, then we're here for constant of 3 because they went linear. One doubled and then the other one doubled. So they have to work in tandem for that. So we know that. That tells us that constant K to the first power. That's what we just figured out by that quick analysis.
Why are you only looking at the first 2 trials and not all?
Okay. They just gave us more data than we needed, really. Let's compare trial 2 and trial 3. We still have the first column the same. So when they did these are actually 6 different experiments. So they mixed it this time. The same amount of NO. But now look over here. We go from 6 to 9. See what I'm saying? And over here we go 1.32 to 1.98. So this time we can look at it and go, compare 1 and 3. So you multiply by 3 to get from 3 to 9, right? If you look at the rate, you'll figure out that 6.60 times 10 to the -5 times 3 is 1.98 times 10 to the -4. It's still linear. They still move the same way. Multiply this by 3, and multiply this by 3. So it's just a really very verification. So you double one, you double the other. You triple one, you triple the other one.
Do you know its first order for this video? So how do you know its first order? Like, how do you know it's K and you can use it?
Let me go here. This column didn't change. This column doubled. And this column doubled. That means the rate and the concentration work together linearly. Make sense? The next step is to look at the data where O3 is the same, which is the last 3. And then this changes. Okay, the NO column starting with 3, comparing 3 and 4, that's a doubling of concentration, right? You see it in the far left column? It's the powers of 10 that makes it hard to just see it. That doubles while this stays the same, so we can ignore this. Look at this. Now, what happened here? Did this double? the rate for 3 and 4 is 1.98 times 2, 3.96. .98 is almost 2, and 3.96 is almost 4. So it did double, right? So all that tells us is it's also first order. So all we're saying is if you keep these the same, these in this column are linear. If you graphed it, it would just be a straight line. Because one doubles, the other one doubles. Triples, this one triples. You see? So that tells you that's first order because it's linear. And same with the second one, we found out the same thing. You double from 3 to 4, you double from 3 to 4 here. Double from 4 to 5, you double from 4 to 5 here. And notice again, all of the O3s are constant for the last 3 data points. You follow that? Sometimes I think I make it sound more complicated than it is. I know that first example I did. That's why I went right past it to get to the meat of things. You guys okay with that? So this is what we're able to discover. This is the rate law for this reaction. Now, doing an experiment like that is how you find out K. So the last part of this is we're going to calculate K. And the way you do this, you can pick any one of those sets of data. It's you can take the data from experiment 1 or the data from experiment 2, the data from experiment 3, doesn't matter which one. I'm just going to use the first one and say concentration of NO equals 1.00 times 10 to the negative 6. Concentration of 3 10 to the negative 6. And then the rate is the last column, 6.60 times 10 to the negative 5. And now we can plug everything in and solve for K. What I'll do is just divide both sides by the concentrations. So I have concentration of NO, concentration of 3, and now we can solve for K by plugging everything in. So if you do an experiment like that, you can find K. There is a more analytical way to look at whether this is first order, second, but it involves graphing it, so I'm saving graphing until next time. But you can look at data when it's simple like that. I mean, if one column was going up by 3.46 and the other one was going up by 3.46, that'd be a lot harder to see just by looking at it. In fact, this was hard to see. That's why you're sitting here confused. This is hard to see because of those powers of 10. I could replace all these with just simple multiples and these with simple multiples, and then it would be obvious. But let me go to have more examples of these. Take slide 8. These are exercises from the back of the book, from the back of the chapter. And the ones that are blue on there are the ones you can look up the answers to. But look at 20. Okay, the decomposition of that acetaldehyde, just think reaction. They're using big words here, but just say concentration. It's second order. It says that. It gives it to you. It's second order. With a rate constant of 4.71, 1 10 to the negative 8. moles per liter per second. It's asked that that equals the rate. Second order, I've basically rewritten this. Rate equals K times the concentration squared. Rate equals K times the concentration squared. I just wrote it really messy. But I'm using this equation. I'm just plugging in that. It tells me that the concentration for this, so that's K. This is the concentration. Moles per liter. So you can just calculate the rate, because you know what the vocabulary is. It tells you at second order, it tells you the concentration. It tells you at second order, it tells you the concentration, and it tells you K, and it asks you to calculate the rate. So we're still just using one of these three. It tells you that it's second order. You didn't have to figure it out. You see that? You okay? Liter per mole per second. That's in liter per mole per second. You've got liter per mole. You ever seen this notation on units to the -1? You sometimes see these written like this, and I notice they do that a lot on the ACS test. I don't tend to do that, but I probably should so y'all see it. But that literally means 55 miles per hour. The -1 puts it on the bottom. In this, when you go liters per mole per second, you've got but I like to write this liters per mole per second. So you got like a triple fraction, but I would rather write this as so I've got molarity on top and second like that. So like I had before, I had concentration on delta concentration of something and delta T. This keeps the concentration units together, it keeps the seconds together. That's the way I would write it instead of like this. I would write it like that. So now we're back to these that you have to figure out the order. All right, look at number 21. On slide 8. Across the top row are 3 different concentrations of the reactant. It's methanol. And then paired with those is 3 rates. So somebody did 3 experiments here. They did it at concentration 44 point whatever, and they had a rate constant of 2. Then they did it at 33 point whatever, concentration stayed the same. Then they did it at 2.2 times 10 to the whatever, concentration stayed the same. So what's the overall order here? 0. Concentration was independent. No, rate was independent of the concentration. This is concentration to the first value. This is concentration squared. This doesn't have concentration. So the rate always stays the same. It just equals the rate constant. Do you see how you can look at that one now and go, okay, that's zeroth order? So now you could go through the calculation. You can pick any one of those. Concentration of methanol. Is that the rate for that way? The rate for all 2.0 times 10 to the negative 2. And the equation is rate equals K times. So you plug in methanol, you plug in rate, and you solve for K. I guess you're going. K is supposed to be units. Concentration. I'll come back to the units. If you see the math now, we can figure out the order, then you know which one of those equations you're supposed to use, and you just plug and shove. You okay with that? Okay, look at 22 on slide 9. Got my slide numbers this time. Okay, look at it. We've got concentration of the reactant in the top row paired with rates in the next row. So what order is that? You'll have to be seeing this by now. In what way does the rate change? It doesn't change. Exactly. But you need to look at the concentrations that go. Is the concentration changing? So the rate is not based on the concentration in any way. So what order is it? 0. Correct. Okay. Look at the next one. Picture that first one in number 23, the 8. Picture that being 0.8. No, I take it back. Move all the decimals, leave that one there, and move the other 2 decimals to the right ones. So you have 832 and 72. So between trial 1 and trial 2, how much does the rate change by a multiple? 8 times something is 32. What is it? 4. So the rate goes up by a multiple of 4. The concentration goes up by a multiple of 2. So which one is it? 0 first or second? Second one. You follow that? You get it now? This went up by a factor of 4, while this went up by a factor of 2. So that means we're in second order. You got it? Another way to say that is K is a constant, so that's not going to change. And I'm just going to say 8. That's the rate there. The rate is up here. 8. And this is right, 1, 0. This 1. So you have this, there's your concentration. This is your rate. And I'm just 7. If I call that 8, and do this one is 32, but that makes sense because if I do 2 times that, that means it ends up being 4 times once I do the square. So then I'm multiplying, this increases by 4. To make that obvious, I have to figure out what k is. So basically, do this 2 times n. This is 2 times n times 2 times n, or 2 times 2 n times n. But the k is what changes this into a different number. But this is where the 4 comes from. It shows up over here. I can explain that well. I thought y'all would see into this. You see what I'm getting at? So we're going through all the different examples now. Slide 10, look at 24. Concentration 1.33. The next concentration is 2.66. That's definitely times 2, right? What's this one? 3.8 goes to, that's 10 to 15.2. Was 15.2 divided by 3.8. So the lower column in number 24, the 3.8, you multiply by 4, you'll get 1.52. I'm skipping the powers of 10. You see the powers of 10? I still say it's the power of 10 that makes this complicated. So what order do you have here? Concentration goes up by 2 and rate goes up by 4. You got it? Huh? Second one. Rate and concentration. The rate is, let's say that's 3, and this is 15, and then this goes up to 30, and this stays 3, this goes up to 45, this stays 3. Rate is constant, it's not dependent on concentration, that's this. The rate has no dependency on the concentration. It just stays the same, it stays constant. This one, let's see, we got 3 and 15, 30. 15 times 2 is 30. 3 times 2 is 6. Well, let's say we got that data. 15 times 3 is 45. 3 times 3 is 9. If you had that data, either here. Now I just did this one. It stays constant. that times 2 is 6. That times 3 is 9. No, I did that right. Fifteen times 2 is 30. 3 times 2 is 6. So both of them went up by a factor of 2. I did that right. And then the last one is do this by concentration, rate, this one went up by a factor of 2, this one went up by a factor of 4. There's 12. And if this goes up by a factor of 2, I want this to go up by a factor of 2, factor of 3. So you multiply between here and here times 2, 15 to 30. Multiply here and here by 4, you get 12. You multiply this by 3, you get 45. You multiply this by 9, you get 27. And so on. This times 3, you get this times 3 squared. So here to here, 15 times 2 is 30. 15 times 3 is 45. But now we're squaring that factor because it's inside the bracket that's squared. So we're squaring that factor and it affects the 8 this way. 3 times 2 squared is 12. And then 3 times 3 squared is 27. That's how this one scales. You guys okay with this? But we won't do any higher orders than that because they do get more ridiculous to follow. All right, some of y'all can do this one. Two concentrations, okay. So look at 26. The first column with numbers in it, and the second column with numbers in it. What stays constant there? The 0.35 and the 0.35. So in this case, we're not looking at the H2, we're looking at the NO. So what's the factor here from this one to this one? 0.3 to 0.6. Factor of 2, so NO concentration increases by a factor of 2. What does that do to the rate? It's because of that power of 10 that you're hating it, I promise. So maybe you want to pull out a piece of paper and work it out. But what's the factor that's increasing by? So I'm multiplying these two things. So x equals, don't scale up by 2. Yeah, this is fine. 1.134. Did y'all see what I did there? You could put that in a calculator and find out what it tells you. If I do one of these operations, -2, maybe it's a little more obvious that you're going to get a whole number. What do you think 2.8 goes into 11 by? These will always come out whole numbers. We're going to do weird fractiony stuff here.
How did you get 0.2?
I changed this. Let me change it back. 2.835 times 10 to the negative 3 is what's in the bottom of column 1. And 1.34 times 10 to the negative 2 is next one in column 2.
Is it 3.9?
Is it what?
Is it like 4?
It is. I think so. I'm going to do this. 128. Yeah. Exactly a factor of 4. So one of them went up by a factor of 2, the other one went up by a factor of 4. So what's the... It's second order for that one. And that was NO. So that gives us rate equals K, NO. That's what we just figured out. That's what we just figured out. You guys with me? What about the other two? Everybody have this up on? Maybe I need to start bringing pages for everybody, because I know y'all in the back can't see unless they have the thing on. Look at the next two columns. Now the top row is the same. And the bottom increases by, that looks like times 2 to me, right there. 0.35 to 0.70, that's times 2. So concentration by a factor of 2. The rate definitely doesn't stay constant, so it's not 0. Question is that a factor of 2? Yeah. 113 times 2 is 226, so that's a factor of 2. So what's the order with respect to this one that's changing H2? Rate went up by a factor of 2, and then concentration went up by a factor of 2. First order. Which means overall we have, H2. Here's our equation. You guys gonna survive this? Integrated rate laws. I'll give you this equation on the test. But this is the integrated rate law. This is the Arrhenius equation, or one form of it. I probably shouldn't have put it there. Just leave that off. But it's this that you use. You can look at this example here and see that this is the equation they're using. All right. Either you figure out that it's first order, or you're flat out told that it's first order. This question says the rate constant for the first order decomposition of this is 9.2 times 10 to the negative 3. per second. How long will it take for 80%? Okay, yeah, I better do this one. This one. So a new equation, I don't mind giving you these equations on the test. Just be able to use them. Two, 4. Okay, this is a very cost. What do we want here? This symbolism is telling us the concentrates. Okay. For this type of problem, assume that's 1 for a concentration. I'm not even going to put the units there. And it's saying how long will it take for 80% of the sample to react and become a C2, to decompose. Again, phrasing these books, we just like to make it sound complicated. So that's a C4H8 decomposing into 2 C2H4s. So how long does it take for 80% of this to decompose? Which means this is A, this is B. So A, if we started at 100, 80% decomposition, meaning 80% of this reaction comes over here, what's left? Well, again, I'm going to go, I think that's the way they did it. That's a simple way to do it. So we've got those two. We've got our equation, natural log. Equals KT. Well, so they give us the rate constant. So they've given us K, so I'm going to divide both sides by K, because they're saying how long will it take. Divide that by K, divide that side by K. It's just T. And then you can solve it. Okay? Your intuition is not going to work with any of these. It's really complicated why these things are what they are. That's why I asked if you took calculus for our class. So I'll give you these equations, just be able to calculate them. Natural log of 1 over 0.80 divided by K. Since you have to use these calculators in here, be sure you understand how they work. Scientific.
So on tests, are we going to have to use these, or can we use our?
Yeah, you have to use those. Because we have problems with people cheating using special calculators that do everything for you. You should at least look at them and get familiar with them. Do you have a really fancy calculator?
I've got a TA4.
Yeah, those are the ones we don't want to
I've got a
use.
Texas Instruments I've used in other chem labs, but I was just curious.
Does it look a lot like this one? I know you want to use the one you're familiar with, but
Yeah, it's fine. I just didn't know.
I'm just saying, you ought to take a look at it before a test. So you don't have to sit there going, where's the log function and stuff like that. I might have to use those because mine's 1 divided by 0.2 natural log divided by 0.2. since your test will be multiple choice, lots do weird things with significant figures. I'm guessing though, I'm going to stick with, those are actually infinite. And K was 2 significant figures. So I guess I'm just going to do that. 70 seconds. Huh, I did it right. Did it the way they did. You guys okay with that? I know your intuition isn't digging into this, but it's not going to. Not without calculus. Okay, this is the same idea, but for second order. And I'll give you these equations. I'll give you, I already messed it up. I started with first order. I don't think they give you these on the ACS test. I'll double check that. Remind me to double check that. First order, second order. What does your intuition tell you for this one compared to that one? Well, it didn't do that, did it? All right, so reaction, butadiene gas. Telling us the rate constant. Initial concentration of butadiene, I'm just going to call it A naught. Concentration A at time t. Is that after time equals and they have this in the unit of minutes too, so we're okay using minutes. You think you could solve this? That's simple, right? Anybody want to try to solve it? Ten to the negative 2. T is 10 minutes. What would you do first? We have to solve for this. Algebra-wise, what would you do first? Really? You're that lost on the algebra? Invert both sides. Concentration equals over. The units off. Times 10 is 1 over 0.2. Point 0.0576 times 10 plus 2. And that's going to be it.
How do you put it all on the bottom?
Why did I put it all on the bottom? Algebra-wise, if you take everything on this side and invert it, and also invert this side, then that's just all of this over 1 inverted. That's just algebra. You guys okay? You enjoying 1152 so far? Zero order. Again, I will give you these equations, just practice with them. Y'all seem very tepid on these equations. I can't make this stuff exciting. I don't know what I could do to wake y'all up. It's plug and chug. And equations I can't explain to you unless you calculus. So I'll give you this on a test. Question is, use data. Oh yeah. So this one turns out, because it's zeroth order, it's linear. Okay, yeah. We're being asked to graphically estimate that. It's going to be a slope. There is a graph on here. It's in the book too, if you can see it. And it's this one I'm looking at, the linear one. They use this in an explanation further in the book. But then they refer us back to here. Do you remember how to find the slope? Like the rise over run. So the rise here, you have to estimate it. They do it here so you can look at what they're doing. But they took 0.0015, which is this bottom here, straight across. so that would be 0.0015. And then they estimated this to be around 0.0028. So they're going so it's this formula for the smoke is that's what they're doing. The rise is the vertical axis, the run is the horizontal axis. And if you look at the graph down here, it goes from 1,000 to 0. So they've got and that estimates K. Collision theory is so conceptual. And I think I've just put y'all to sleep, but kind of don't want to do it now. So it's been a lot of equations up to now. You should be practicing what I've gone over in here, and I've put the PowerPoints up. And I am going to get questions like these on D2L so you have more practice. I put the test on the 23rd. Is that right? Don't wait to start going over this stuff. At least the way I feel now, that y'all are not really engaged with it. This is exactly what you're going to have to do for a test, what I'm doing up here. You guys going to be all right? And we'll start with collision theory next time. Did I ask you guys if you did intermolecular forces last semester? I thought my class did. I'll look at what's coming up and see if I can give you a little hope. I can pep it up for equilibrium a little bit. Because that equation, that basic equation has some intuition. More than these do. Y'all going to be okay practicing these? Anybody think you need help? Well, if you do, get with me or get with our SI. But don't wait if you're feeling lost on it. If I give you the equation, all you have to do is be able to read the question and figure out what it's asking and be able to plug in. We'll do a little bit of this graphical stuff